All right, we're about to explore a connection that sounds, well, a little wild. We're going to look at how the ancient, kind of messy process of burning sugar inside a cell has a deep structural connection to how artificial intelligence actually thinks.
Yeah, it's a fair question, right? I mean, on the surface, absolutely nothing. One is just the brute force of biology, and the other is the absolute cutting edge of computers. But as we're about to see, they both have to solve the exact same problem. How do you take raw potential and make it useful? And this quote, this really gets to the heart of it. We love to focus on the elegant, smart parts of any system, the mitochondria making all the energy, or the reasoning part of an AI. But the real work, that essential first step, happens way earlier in a much more primitive and, well, brutal stage. So that's the big idea we're unpacking here. Intelligence, whether it's in a living cell or in a computer chip, doesn't start with some act of clean creation. Nope. It starts by taking something whole and breaking it down in a very, very specific way. Okay, so our first stage is all about trapping potential. Before any system can do its fancy work, it first has to grab a resource and, crucially, make sure that resource can't get away. This whole idea of commitment is the key. So picture this. On the left, you've got a glucose molecule, basically just locked up solar energy, and it drifts into a cell. On the right, you have raw text, just words full of potential meaning, being fed into a large language model. In both cases, the very first step is almost identical. The cell performs something called phosphorylation, which is basically just tagging the sugar with a chemical marker. And the LLM? It does tokenization, breaking down the text into little numerical pieces. Both are fundamentally an act of transformation. We call this first vital step commitment. And here's the part that's just fascinating. Both systems have to spend energy right up front. The cell literally burns one of its precious ATP molecules, and the AI uses up computational power. They're not getting anything out of it yet. They are paying a price just to trap the resource. So here's how that commitment actually works. First, you tag it. The cell sticks a phosphate group onto the glucose. The AI shatters text into numerical tokens. This step destroys the original form. That glucose is now a new chemical, and the text isn't really natural language anymore. And second, that tag traps the resource. The tagged glucose physically can't get back out of the cell, and those tokens can't be perfectly put back together into the original nuanced text. This quote just says it all, doesn't it? The glucose, or the text, it doesn't belong to the outside world anymore. It's been captured. It now belongs completely to the internal machinery of the system. It's inside the computational cytosol. So the resource is trapped. Now the next step is completely counterintuitive. You'd think the system would start using it, right? Wrong. Both systems spend even more energy not to use the resource, but to make it fundamentally unstable, to make it ready to break. In glycolysis, the cell burns another ATP molecule to slap a second phosphate tag on the sugar. This makes the whole thing incredibly unstable. Meanwhile, in an LLM, the tokens are projected into this crazy, complex map of meaning called an embedding. Now it's not just a number, it's a location, a point in space defined by its relationship to every other word. Both of these steps are expensive, they're irreversible, and they're both designed to prepare for one thing, a split. And all this leads to a state we can call structured instability. See, the goal isn't just to tag the resource anymore, it's to completely change its nature. That double-tagged sugar is now just begging to split in half, and the token embedding is now defined not by what it is, but where it is in relation to everything else. This phrase from the source just nails it. You're no longer asking, what word was this? You're asking, what is this word like? The system literally destroys the surface identity to create a map of relationships, a geometry of meaning. That's exactly what an embedding is. Okay, so we've trapped our resource and we've made it super unstable. The next logical step is it breaks. And this brings us to our third stage, forcing all the broken little pieces to speak the same common language. So when that double tag sugar finally splits, it creates two different 3-carbon molecules. But here's the thing, the cell's machinery can only process one of them. So what does it do? It immediately converts the wrong one into an identical copy of the right one. That's isomerization.
In an LLM, the attention mechanism does something weirdly similar. It looks at all the different word embeddings and decides which ones matter most to each other in this specific sentence, forcing them all into a shared frame of relevance so they can be compared and combined. And that gets us to this crucial idea: representational uniformity. Before you can do any really complex work, you have to convert everything into a standard format. It's the old apples and oranges problem. You can't compare them until you convert them both into something standard, like calories or weight, a standard unit of computation. And boom, there it is. That's the punchline of the whole analogy. That standardized 3-carbon sugar molecule, that is, for all intents and purposes, the fundamental token of metabolism. It's the universal currency that the rest of the cell is built to understand, just like the outputs of an attention layer are the tokens of thought for an AI. All right, now we get to the really big reveal. We've seen all these messy, destructive, energy-burning steps. What is the actual point of all this? I mean, think about it. We're all taught in school that glycolysis is about making ATP for energy, and we assume in LLM's front end is about, figuring out the meaning of the text. But what if both of those assumptions are missing the real point entirely? If you look at the books for glycolysis, the cell actually spends 2 ATP molecules and only gets 4 back. That's a tiny, tiny net gain. So the little bits of energy produced along the way, they can't be the main product. It just doesn't make sense. And this is just such a powerful way to reframe it. That little bit of energy gain isn't the profit. It's the rent. It's just enough to pay the bills and keep the lights on in this brutal, inefficient factory. It's just the cost of doing business. The real product is the standardized output. It's the canonical token. Glycolysis isn't really an energy factory. It's a representation factory. Its entire job, its whole purpose, is to take a messy, unusable resource from the outside world and create a standardized input that the more advanced systems, like the mitochondria, can actually understand and work with. So let's just zoom out for a second. What does this incredibly deep structural similarity between a metabolic pathway and a neural network actually tell us about the nature of intelligence itself? Well, it tells us that intelligence isn't built from the top down. It claws its way up from the bottom. You simply cannot have the elegant energy production of the mitochondria without the messy, destructive work of glycolysis happening first. And you absolutely cannot have the complex reasoning of an AI without first shattering language into tokens and embeddings. In both of these worlds, the universe doesn't seem to design for elegance. It designs for what works. It breaks things over and over again until something is created that can just keep going. And that's really the final provocative thought to leave you with. Whether you're looking at a cell or at a piece of silicon, the path to creating meaning, to creating intelligence, it isn't some clean act of creation. It's an act of controlled destruction. It's about taking the infinite, pure potential of the world and forcing it through a narrow, costly, brutal constraint until something useful, something that can keep the whole system moving, finally emerges on the other side.